This is problem 50 from the 9th edition of Cutnell. My right hand is broken, so this is going to be pretty messy. So the problem is to verify her suspicion that a rock specimen is hollow. A geologist weighs the specimen in air and in water. She finds the specimen weighs twice as much in air as it does in water. The density of the solid is 2.24 times 10 to the third boy, that's bad. 2.24 times 10 to the third kilograms per meter cubed. What fraction of the specimen's apparent volume is solid? Okay, so we know that it weighs twice as much in air as it does in water. So what does it weigh in water? Let's think about a free body diagram. So the forces acting on it in water are mg down and the buoyant force up. And so the buoyant force, if you are trying to see what the apparent weight is, the buoyant force kind of dilutes part of the actual weight. So the apparent weight apparent, will be mg minus the buoyant force. And that's half as much as the weight in air. So the weight in air is just mg. So we know that mg minus the buoyant force, that's the apparent weight, equals half of mg. With a buoyant force equals 1/2 mg. What else do we know about the buoyant force? We know that the buoyant force equals the weight of the fluid displaced. And in this case, the fluid that's displaced is water. So in this case, it'll be the weight of the water that's displaced. Well, the weight of the water that's displaced is going to be the density of water. I'll just put a W for water. The density of water times the volume of water. Well, the volume that'll be displaced is the same as the total volume of our object. So the buoyant force will be the weight of the water, the density of the water, oops, I forgot a G, rho G, will be the density of the water times the volume of the water times G. And that's because density equals mass over volume. So when I'm trying to get the mass of the water here, when I'm trying to get the mass of the water, I can replace it with the density of the water times the volume of the water. And that's what I did right here. So this is just mg, where m is the mass of the water. Okay, so we know that the buoyant force equals 1/2 mg. We also know that the buoyant force equals the density of water times the volume of water times g. So we know that 1/2 mg equals the density of water times the volume of water times G. So our G's can cancel. And also we know that the volume of the water displaced is the same as the volume of our object. So 1/2 m, and m is the mass of our object, equals the density of water times the volume of our object. Let's put volume object. And we can say that if we look at our object as our whole, our total volume over our mass or I said total volume, we can just call that volume of our object the way we did over on the other side. But the volume of our object over our mass actually I'm not sure I'm going to need that, so we'll come back to that if we need it. So we know that the density of our material that we're looking at equals the mass of our material over the volume of the object that's just made up of our material. So just the part that's made up of our material. And let's see, if we look over here at this equation, and I solve for V of the object, so I'll call that V of the object. That equals the mass over 2 rho water. And then going back to this part right here, we know that our mass equals the volume of our material times the density of our material. So volume of our material means just the volume that's just made up of the solid substance, and not the total volume, whereas the volume of the object is the total volume. So now I can say the volume of my object, I'm plugging in for the mass here, equals the volume of my mass times the density of my mass over 2 times the density of water and what I'm looking for here is the fraction of the volume that is made up of the solid material. And so I'm looking for the volume of what I've been calling material over the total volume. So if I multiply both sides by 2 rho water, divide both sides by rho material, and then also divide both sides by rho of the object, and I get volume of the material over the volume of the object, and the density of water is 1,000 kilograms per meter cubed. And in the problem that I was given, whoa, that's a meter cubed. In the problem that I was given, the density of the solid material was 2.24 times 10 to the third, or 2,240, sorry. That's a 4. Can't ever write 4s with a broken arm or without one. So 2,240. See if I can get a 4 this time. Kilograms per meter cubed. And then if I do that division, I get 0.819. If I did my, no, I didn't. I never do my math right on the calculator. That's the hard part. Okay, so 2,000 divided by 2240 is 0.89. And that's a 9. I can do this 0.89. So try to pretend that that's 0.89. As you've been trying to pretend that all my writing all along has been what it is. And that's the end of this problem.